Imagine for a moment that you've spent your entire career studying the solar system's largest planet. You've written textbooks about it. You've built mathematical models describing its every layer, from its swirling cloud tops down to its presumed rocky core at the center. You understand Jupiter the way an architect understands a building they've designed. And then one day, a spacecraft sends back measurements that tell you something impossible, something that shouldn't exist, something that makes you question everything you thought you knew about how planets are built. The heart of Jupiter, the very foundation upon which this gas giant stands, is not what it should be. It's blurred, mixed, diluted, as if someone took the neatly organized layers you expected and stirred them like paint in a bucket. And this isn't just strange, this is revolutionary. Because if Jupiter, the most massive planet in our solar system, the gravitational anchor that has shaped the orbits of countless worlds, doesn't follow the rules we've established, then what does that say about our understanding of planetary formation itself? What does it say about the thousands of exoplanets we're discovering around other stars? What does it say about the very processes that built the solar system we call home? This is the story of how a single spacecraft, Juno, traveling through the most hostile environment in the solar system, discovered that Jupiter has been hiding a secret for 4.5 billion years. And this secret is forcing scientists to reconsider everything they thought they understood about how giant planets come to be. But before we dive into this mystery, if you enjoy content that explores the most mind-bending discoveries in space science, make sure you hit that subscribe button and turn on notifications so you never miss an episode. We're going to be exploring some of the universe's most fascinating puzzles, and I'd love to have you along for the journey. So what exactly did Juno discover? To understand why scientists are so shocked, we first need to understand what they expected to find. For decades, our model of Jupiter was relatively straightforward. Picture it like this. At the very center, you'd have a dense core made of rock and ice, perhaps 10 to 20 times the mass of Earth, compressed into a sphere roughly the size of our planet. This core would be incredibly hot, reaching temperatures of 35,000 degrees Fahrenheit, about as hot as the surface of the sun. Around this core, you'd have distinct layers, like the layers of an onion. First would come a shell of metallic hydrogen, a bizarre state of matter that only exists under extreme pressure, where hydrogen atoms are squeezed so tightly that their electrons break free and the hydrogen becomes electrically conductive like a metal. Above that would be a layer of liquid molecular hydrogen, still under immense pressure but not quite metallic. And finally you'd reach the outer atmosphere, the part we can actually see, with its famous bands of color and the great red spot storm that has raged for centuries. This model made sense. It fit with how we understood planets to form. Heavy elements sink to the center during formation, creating a dense core. Lighter elements like hydrogen and helium float on top in distinct layers. It's basic physics, density stratification, the same principle that makes oil float on water. But Juno's measurements revealed something fundamentally different. The spacecraft, orbiting Jupiter in a highly elliptical path that brings it incredibly close to the planet's cloud tops, used extraordinarily precise gravity measurements to peer deep into Jupiter's interior. And what those measurements showed was stunning. Jupiter's core isn't a neat, compact ball of heavy elements. Instead, heavy elements, things like rock and ice and metals, are spread throughout a vast region that extends from the very center of the planet outward to nearly half of Jupiter's radius. Think about that for a moment. Jupiter has a radius of about 70,000 kilometers. That means heavy elements are distributed across a zone that reaches out 35,000 kilometers from the center. This diluted core, as scientists call it, contains somewhere between 10 and 45 Earth masses worth of heavy elements. But they're not concentrated in one place. They're mixed with the hydrogen and helium that make up most of Jupiter's mass. It's as if you took that dense rocky core, that neat pit at the center, and somehow stirred it into the surrounding layers, creating a fuzzy, blurred boundary between the core and the envelope above it. How could something like this even form? Why hasn't this structure settled over billions of years? What if we're not looking for the answer in the right place? These are the questions that have consumed planetary scientists since Juno's discoveries were announced. And the answers, as we'll see, take us on a journey through some of the most violent and dramatic events in the history of our solar system. Let's step back for a moment and talk about Jupiter itself, because to understand why this discovery is so shocking, we need to understand what Jupiter is and how scientists thought it came to be. Jupiter is not just big, it's incomprehensibly massive. It contains more mass than all the other planets in the solar system combined. If you could somehow gather up Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and every moon, asteroid, and comet, and pile them all together, you'd still need to multiply that mass by more than 2 to match Jupiter. In fact, Jupiter is so massive that it almost became a star. If it had been about 80 times more massive, the pressure and temperature at its core would have been sufficient to ignite hydrogen fusion, turning it into a second sun. Some scientists even refer to Jupiter as a failed star, though that's not entirely accurate. It's more precise to say that Jupiter is the most massive object in our solar system that didn't quite make it to stellar status. This enormous mass gives Jupiter extraordinary influence over the solar system. Its gravity has shaped the orbits of countless objects. The asteroid belt between Mars and Jupiter. Jupiter's gravity is largely responsible for preventing those asteroids from coalescing into a planet. The comets that occasionally streak across our skies, many of them were gravitationally flung into the inner solar system by encounters with Jupiter. Jupiter has acted as both a shield and a scythe, sometimes protecting Earth from impacts by capturing or deflecting incoming objects, and sometimes sending them careening toward us. Understanding Jupiter isn't just about understanding one planet. It's about understanding the architecture of our entire solar system. For most of human history, Jupiter was just a bright wandering star in the night sky. The ancient Greeks called it Zeus, king of the gods. The Romans called it Jupiter, their own king of gods. But it wasn't until 1610, when Galileo Galilei pointed his primitive telescope at the planet, that humans first saw Jupiter as more than a point of light. Galileo discovered 4 large moons orbiting Jupiter, a revolutionary observation that helped prove that not everything in the universe orbited Earth. Over the following centuries, astronomers learned more and more about Jupiter. They mapped its cloud bands. They observed the Great Red Spot. They discovered more moons, but they couldn't see beneath the clouds. They couldn't peer into Jupiter's interior. That required different tools, different methods, different kinds of observation. The breakthrough came with the space age. The Pioneer and Voyager spacecraft, flying past Jupiter in the 1970s, sent back the first close-up images and measurements. The Galileo probe, which orbited Jupiter from 1995 to 2003, provided even more detailed data, including the first direct measurements of Jupiter's atmosphere when it sent a probe plunging into the planet's clouds. All of these missions helped scientists refine their models of Jupiter's interior structure, but there were limits to what they could learn. Seeing inside a planet is extraordinarily difficult. You can't drill into it like geologists drill into Earth. You can't send seismometers to detect internal vibrations like we do to study Earth's interior. Instead, scientists have to rely on indirect measurements, particularly gravity. Here's why gravity is so important. The way a planet's gravity field behaves tells you how mass is distributed inside that planet. If all of Jupiter's mass were concentrated at a single point at its center, the gravity field would be perfectly symmetrical, identical in all directions. But planets aren't point masses. They're extended bodies with complex internal structures, and that complexity shows up in subtle variations in their gravity fields. By measuring these variations with extraordinary precision, scientists can create models of what the interior must look like. Think of it like this. Imagine you're blindfolded and someone hands you a wrapped present. You can't see what's inside, but by shaking it, feeling its weight distribution, and noting how it responds when you move it, you can make educated guesses about what's in there. Is it dense and solid, loose and shifting, carefully packed? The same principle applies to studying planetary interiors, except instead of shaking the planet, we measure how spacecraft are accelerated by the planet's gravity as they fly past or orbit it. These measurements need to be incredibly precise. We're talking about detecting changes in a spacecraft's velocity as small as 0.01 millimeters per second. That's about the speed of a snail. To achieve this, scientists use radio signals. As a spacecraft flies past Jupiter, it continuously sends radio signals back to Earth. By measuring tiny changes in the frequency of those signals, a phenomenon called the Doppler effect, scientists can determine exactly how the spacecraft's velocity is changing. Those changes are caused by variations in Jupiter's gravity field, which in turn are caused by how mass is distributed inside the planet. It's an elegant technique, but it requires exquisite precision and careful analysis. Before Juno, scientists used these gravity measurements from earlier missions to build models of Jupiter's interior, and those models suggested something relatively straightforward. Jupiter should have a compact core of heavy elements, surrounded by distinct layers of different forms of hydrogen and helium. The core might be 10 to 20 Earth masses, fairly dense, clearly separated from the envelope above it. This made sense within the framework of how scientists understood planets to form. The story of planet formation begins with a disk of gas and dust orbiting a young star. Within that disk, small particles of dust and ice stick together through electrostatic forces and gentle collisions, gradually growing into pebbles, then boulders, then larger and larger bodies. This process is called accretion. For terrestrial planets like Earth, accretion continues until you have a planet-sized body made mostly of rock and metal. But for giant planets like Jupiter, there's an additional step. Once the growing core reaches a critical mass, somewhere between 5 and 20 Earth masses depending on conditions, it becomes massive enough to gravitationally capture gas directly from the surrounding disk. At first, this gas accretion is slow. The growing planet has a small atmosphere that gradually thickens. But once the mass of the captured atmosphere equals the mass of the solid core, something dramatic happens. The planet reaches what's called the critical mass, and gas accretion becomes runaway. The planet rapidly balloons in size, capturing enormous amounts of hydrogen and helium from the disk around it. This runaway phase continues until either the gas disk dissipates, which happens when the young star's stellar wind blows away the remaining gas, or until the planet becomes so massive that it carves a gap in the disk around itself, cutting off its own supply. This core accretion model has been the dominant theory of gas giant formation for decades. It explains a lot of what we observe. It explains why Jupiter is so massive compared to the terrestrial planets. It explains why Jupiter is enriched in heavy elements compared to the Sun, because that heavy element core formed first, before the gas was captured. It explains the timing of Jupiter's formation, which needs to happen within the first few million years of the solar system's history, before the gas disk disappears. The model has been refined and improved over the years, with more sophisticated physics and better equations of state describing how matter behaves under extreme conditions. But the fundamental picture has remained the same. Form a solid core first, then capture gas. Heavy elements at the center, hydrogen and helium on top. Distinct layers. That's how you build a Jupiter. Or, so scientists thought. Because when Juno arrived and started making its incredibly precise measurements, the data didn't fit this picture, not even close. And that's when the real mystery began. The Juno spacecraft is one of the most remarkable machines humanity has ever sent to another planet. Launched in August 2011 from Cape Canaveral, Florida, aboard an Atlas V rocket, Juno embarked on a nearly 5-year journey, covering 2.7 billion kilometers to reach Jupiter. The spacecraft is about the size of a basketball court when its 3 enormous solar panels are fully deployed. Those solar panels, incidentally, are the largest ever sent on a planetary mission, necessary because Jupiter receives only about 4% of the sunlight that Earth does. At that distance from the Sun, solar power is challenging, but Juno's designers managed to make it work, generating enough electricity to power the spacecraft's instruments and systems. The mission is named after the Roman goddess Juno, wife of Jupiter, which is fitting given the mythology. According to the myth, Jupiter drew a veil of clouds around himself to hide his mischief. But Juno was able to peer through the clouds to see Jupiter's true nature. The spacecraft Juno is doing much the same thing, using its instruments to look beneath Jupiter's cloud tops and reveal the planet's hidden interior. Juno's journey to Jupiter was carefully choreographed. The spacecraft first flew past Earth in October 2013, using our planet's gravity to slingshot itself toward Jupiter with increased velocity. This gravity assist maneuver is a common technique in spaceflight, allowing missions to reach distant destinations without requiring impossibly large amounts of fuel. After the Earth flyby, Juno continued its journey through the solar system's asteroid belt and out toward Jupiter's orbit. Finally, on July 5, 2016, Juno arrived. This was perhaps the most critical moment of the entire mission. As Juno approached Jupiter, the planet's gravity accelerated the spacecraft to speeds of over 200,000 kilometers per hour. To enter orbit rather than flying past, Juno had to fire its main engine for 35 minutes, slowing down just enough to be captured by Jupiter's gravity. This orbit insertion burn was a tense event. The spacecraft was operating autonomously, too far from Earth for real-time commands. Mission controllers could only watch and wait as the signals, taking nearly an hour to travel from Jupiter to Earth, finally confirmed that Juno had successfully entered orbit. The relief and celebration at Mission Control were palpable. After a 5-year journey, Juno had arrived at its destination, ready to begin its scientific investigation. But arriving at Jupiter was just the beginning of Juno's challenges. Jupiter is surrounded by the most intense radiation environment of any planet in the solar system. This radiation comes from Jupiter's immense magnetic field, which is about 20 times stronger than Earth's and extends millions of kilometers into space. Charged particles, mostly electrons and ions, are trapped by this magnetic field, creating radiation belts similar to Earth's Van Allen belts, but far more dangerous. These high-energy particles can damage electronic equipment, degrade solar panels, and cause all sorts of havoc for spacecraft. To survive, Juno was equipped with a radiation vault, a titanium box nearly 1 centimeter thick that houses the spacecraft's most sensitive electronics. Even with this protection, Juno's mission lifetime is limited by the cumulative radiation exposure it receives during each close pass of Jupiter. The spacecraft's orbit was carefully designed to minimize time in the most intense radiation zones. Juno follows a highly elliptical polar orbit, swooping in close to Jupiter's cloud tops every 53 days and then swinging out far from the planet before coming back for another pass. At its closest approach, called perigove, Juno comes within about 4,000 kilometers of Jupiter's cloud tops, skimming just above the atmosphere. At its farthest point, the spacecraft travels out to about 8 million kilometers from Jupiter, far beyond the orbits of Jupiter's large moons. This orbit gives Juno brief but intense opportunities to make its measurements while limiting radiation exposure. The key to Juno's investigation of Jupiter's interior is gravity science. The spacecraft carries no dedicated gravity instrument because the instrument is essentially the spacecraft itself, along with the ground-based radio tracking stations of NASA's Deep Space Network. Here's how it works. As Juno flies past Jupiter during each perigove pass, the planet's gravity pulls on the spacecraft, accelerating it in complex ways that depend on the internal mass distribution. By continuously tracking Juno's radio signal from Earth, scientists can measure incredibly tiny changes in the spacecraft's velocity by observing Doppler shifts in the radio frequency. The technique is so precise that it can detect velocity changes as small as a fraction of a millimeter per second. Think about that for a moment. Jupiter is 300 million kilometers away, and we're measuring velocity changes comparable to the speed of a slowly crawling insect. This requires not only advanced technology, but also careful accounting for all the other forces acting on the spacecraft, including solar radiation pressure, the gravitational influence of Jupiter's moons, and even the tiny thrust from leaking propellant. Every factor must be modeled and removed from the data to isolate the signal from Jupiter's gravity field. Over multiple orbits, as Juno passes over different parts of Jupiter, these measurements build up a detailed map of the planet's gravity field. The gravity field is described mathematically using a series of harmonic coefficients, numbers that describe how the gravity deviates from a perfect sphere. Lower-order coefficients tell you about the overall shape and large-scale structure. Higher-order coefficients reveal smaller features and asymmetries. By analyzing these coefficients and comparing them with theoretical models of planetary interiors, scientists can work backward to figure out what the inside of Jupiter must look like. Juno carries 8 other scientific instruments beyond the gravity experiment. There's a microwave radiometer that can peer beneath the clouds to measure the abundance of water and ammonia at different depths. There's an infrared spectrometer to map Jupiter's heat emission and study the composition of its atmosphere. There's an ultraviolet spectrograph to observe Jupiter's auroras, the spectacular light shows that occur at the planet's poles when charged particles from the magnetosphere collide with the atmosphere. There are instruments to study Jupiter's magnetic field in detail, measuring both its strength and its structure. And there's JunoCam, a visible light camera that was originally included primarily for public outreach, but has proven scientifically valuable as well, capturing stunning images of Jupiter's swirling clouds and atmospheric features. All of these instruments work together to build a comprehensive picture of Jupiter, from its interior to its atmosphere to its magnetosphere. But it was the gravity measurements, more than anything else, that revealed the shocking truth about Jupiter's core. And those measurements began to come in during Juno's first few orbits. The first scientific results from Juno were published in May 2017, less than a year after the spacecraft entered orbit. The papers, appearing in the prestigious journal Science, presented a Jupiter that was both familiar and alien. The familiar parts included spectacular images of Jupiter's poles, showing clusters of cyclones in geometric arrangements unlike anything seen elsewhere in the solar system. The measurements of Jupiter's magnetic field revealed it to be even more complex and asymmetric than expected, suggesting that the field is generated by processes occurring in multiple layers within the planet. The microwave observations showed that Jupiter's colorful cloud bands extend deep into the atmosphere, with the jet streams that drive the weather reaching down thousands of kilometers below the visible cloud tops. All of this was fascinating, but it was the gravity measurements that were truly revolutionary. The data showed something that didn't match any of the existing models of Jupiter's interior. To understand what the scientists found, we need to talk about what they were measuring. The gravity field coefficients that Juno measured revealed that Jupiter's interior is more extended, more spread out than it should be if there were a compact core at the center. Specifically, the measurements suggested that heavy elements are present not just in a small central core, but distributed throughout a large region of the planet's interior. At first, scientists weren't entirely sure what to make of this. Gravity measurements alone don't give you a unique solution. Different interior structures can potentially produce similar gravity fields. So the scientists constructed multiple models, trying different configurations to see which ones could match Juno's measurements. They tried models with compact cores of different sizes. They tried models with partially dissolved cores, where some heavy elements had mixed into the envelope above. They tried models with extended cores, where heavy elements were spread across a larger region. What they found was striking. The only models that could adequately fit Juno's gravity measurements were those with a dilute core, where heavy elements were distributed across a zone extending to about half of Jupiter's radius. The total mass of heavy elements could be anywhere from 10 to 45 Earth masses, depending on the specific model. But regardless of the exact number, these heavy elements were not concentrated in a compact ball at the center. They were spread out, mixed with the hydrogen and helium that makes up most of Jupiter's mass. This was completely unexpected. Nothing in the standard models of planet formation predicted such a structure. And the more data Juno collected over subsequent orbits, the more certain scientists became that this dilute core was real. By 2019, when additional analyses were published in the journal Nature, the scientific community had largely accepted the reality of Jupiter's fuzzy core. The question was no longer whether the dilute core existed, but how it got there. And this is where things get really interesting, because explaining the dilute core requires rethinking our understanding of Jupiter's history. How could something like this even form? The problem is that according to standard planet formation theory, heavy elements should naturally segregate to the center. During the formation process, as the planet grows and heats up, denser materials sink while lighter materials rise. This is the same process that created Earth's iron core. The heavy elements shouldn't remain mixed with the hydrogen and helium. They should settle, and they should settle relatively quickly, at least on geological timescales. Even if the core somehow started out diluted, you'd expect it to compact over time. Jupiter is 4.5 billion years old. That's an incredibly long time for materials to separate according to density. Yet, the dilute core remains. Why hasn't this structure settled over billions of years? This question puzzled scientists when the discovery was first announced. and it continues to be a major focus of research today. There are really only a few possibilities. Either something happened to Jupiter after it formed that disrupted its core and created the dilute structure, or the dilute core is somehow a natural consequence of processes occurring within Jupiter, even today. Or we're fundamentally misunderstanding something about how giant planets form and evolve. Let's explore these possibilities, starting with the most dramatic and perhaps most intriguing explanation: the giant impact hypothesis. In August 2019, a team of scientists led by Shangfei Liu from Sun Yat-sen University in China published a paper in the journal Nature that proposed a radical explanation for Jupiter's dilute core. What if Jupiter was hit, not by a small asteroid or comet, but by another massive planet? A head-on collision between the young Jupiter and a large planetary embryo, roughly the size of Uranus or Neptune, could have shattered Jupiter's primordial core and mixed the heavy elements deep into its interior. This wasn't just speculation. Liu and his team ran detailed computer simulations of such an impact, modeling the physics of how two massive bodies would interact and how the resulting planet would evolve over billions of years. And what they found was remarkable. A sufficiently energetic impact could indeed produce an interior structure consistent with what Juno observed. Let's think about what this would have looked like. The early solar system, about 4.5 billion years ago, was a much more chaotic place than it is today. The planets were still forming, growing through collisions with smaller bodies and occasionally with each other. Planetary embryos, protoplanets that had grown to significant size but hadn't yet become full planets, wandered the solar system on unstable orbits. Jupiter, already massive, would have had a strong gravitational influence on these objects, perturbing their orbits and sometimes sending them on collision courses. Now imagine a planetary embryo perhaps 10 times the mass of Earth, primarily composed of rock and ice, approaching Jupiter. As it gets closer, Jupiter's gravity accelerates it to enormous speeds, perhaps 150,000 kilometers per hour or more. The impact, when it comes, is not a glancing blow, but a direct hit, head-on. The energy released is almost incomprehensible. For a moment, let's put this in perspective. When the asteroid that killed the dinosaurs struck Earth 66 million years ago, it released energy equivalent to billions of nuclear weapons. That impact was devastating, but it involved an object only about 10 kilometers across hitting Earth. Now, we're talking about a body 10 times Earth's mass, hitting Jupiter at speeds that make the dinosaur killer look like a slow-motion pebble. The energy released would be measured in units that strain human comprehension. What happens in such an impact? Liu's simulations show that the impactor, despite being enormous by terrestrial standards, is essentially like a bullet passing through Jupiter. It plunges through Jupiter's gaseous outer layers, which offer relatively little resistance, and slams into Jupiter's core with tremendous force. The core, which at this point in Jupiter's history would have been a relatively compact ball of rock and ice, shatters. The material from both the impactor and Jupiter's original core is dispersed throughout the planet's deep interior, mixing with the metallic hydrogen that exists at those depths. Over the course of just hours, Jupiter's core transforms from a neat, compact structure into a diluted, fuzzy one, with heavy elements spread across a vast region. But here's the really interesting part. The dilute core doesn't quickly settle back into a compact structure. You might think that over time, the heavy elements would sink back toward the center, gradually reforming a compact core. But Liu's simulations showed that this doesn't happen, at least not on timescales shorter than billions of years. The reason has to do with the internal structure of Jupiter and the way heat and material move within the planet. In Jupiter's deep interior, the conditions are so extreme that the behavior of matter becomes counterintuitive. The pressure is millions of times Earth's atmospheric pressure. The temperature is tens of thousands of degrees. Under these conditions, hydrogen takes on that bizarre metallic form, behaving like a liquid metal rather than a gas. The movement of material through this region is governed by convection, where hot material rises and cool material sinks, similar to the way water circulates in a boiling pot. But the details of this convection and how it affects the distribution of heavy elements depend on subtle factors like the miscibility of different materials, meaning whether they mix together or separate like oil and water. and the rate at which heat is transported. Liu's team found that if a giant impact mixed heavy elements into Jupiter's deep interior, creating a gradient where the concentration of heavy elements decreases gradually from the center outward, this structure could remain stable for billions of years. The heavy elements wouldn't quickly sink back to form a compact core. They would remain distributed across a large region, exactly as Juno observed. The giant impact hypothesis was compelling for several reasons. First, it explained the observations. The dilute core structure that Liu's models produced matched what Juno's gravity measurements suggested. Second, it was plausible. We know that giant impacts were common in the early solar system. Earth's moon is thought to have formed from the debris of a giant impact between the proto-Earth and a Mars-sized body. Uranus's unusual tilted rotation, where its axis is nearly perpendicular to its orbital plane, is likely the result of one or more giant impacts. Venus's slow backward rotation might also be explained by impacts, so the idea that Jupiter could have experienced a major collision isn't far-fetched. Third, the hypothesis made testable predictions. If Jupiter had been hit by a large impactor, that event might have had other consequences beyond just disrupting the core. It might have affected Jupiter's rotation rate, its atmospheric composition, or other observable properties. Scientists could look for these signatures in the data. The paper attracted significant attention. Here was a dramatic explanation for a puzzling observation, backed by sophisticated computer modeling. News outlets around the world ran stories about Jupiter's violent past, often with eye-catching artist illustrations showing the moment of impact. The scientific community was intrigued but cautious. The simulations were impressive, but they necessarily made simplifications. Could a more detailed model, with better physics, still produce a stable dilute core? And was a giant impact really the only explanation? To test the giant impact hypothesis more rigorously, scientists needed to run even more detailed simulations. The original Liu et al. Study had used sophisticated modeling techniques, but there were still approximations involved, particularly in how the different materials mixed during and after the impact. Understanding the behavior of matter under the extreme conditions found deep inside Jupiter is extraordinarily challenging. We're talking about pressures and temperatures that are difficult even to create in laboratory experiments, let alone to fully model in simulations. So other research groups began working on the problem, using different approaches and more advanced computational methods. One key question was whether the dilute core structure would remain stable over billions of years. In the years following Liu's paper, several research teams investigated the long-term evolution of Jupiter's interior. What they found was complex. The stability of a dilute core depends sensitively on how heat is transported through Jupiter's interior, and on whether heavy elements can easily mix with or separate from the surrounding hydrogen. If the heavy elements are immiscible, meaning they don't mix well with metallic hydrogen, they would tend to separate and sink over time. If they're miscible, they would remain mixed. The behavior depends on the specific forms of heavy elements involved, whether they're rocky silicates, water ice, or metallic iron, and on the exact conditions of temperature and pressure. Different elements behave differently under these extreme conditions, and that complexity makes the problem difficult to solve definitively. Then, in 2025, a bombshell. A new study, led by researchers at Durham University and using some of the most sophisticated planetary impact simulations ever performed, challenged the giant impact hypothesis. The team used high-resolution models that tracked the behavior of different materials, rock, ice, hydrogen, and helium, with improved physics describing how they mix and separate during an impact. They ran numerous simulations, testing different impact scenarios, different impactor masses, different impact angles, and different velocities. What they found was striking. In none of their simulations did a giant impact produce a stable dilute core structure like the one Juno observed. Instead, they found that the heavy materials from the core, even when initially dispersed by the impact, quickly resettled. The rock and ice didn't remain mixed with the hydrogen for billions of years. They separated, maintaining a distinct boundary between the core and the outer envelope. The dilute core structure that Liu's simulations had produced, it appeared, might be an artifact of the simplified physics used in those earlier models. This new research didn't prove that a giant impact couldn't explain Jupiter's core. Science rarely deals in absolute proof, but it raised serious doubts. If even the most extreme impact scenarios couldn't produce a stable dilute core in these improved simulations, then perhaps the giant impact hypothesis wasn't the right explanation after all. The Durham team suggested that Jupiter's dilute core more likely formed gradually during the planet's growth and evolution, rather than catastrophically through an impact. But this brought scientists back to the original problem. How do you form a dilute core gradually through standard planet formation processes? And if Jupiter has one, why would Saturn also show evidence of a similar structure? Because that's another fascinating twist in this story. The Cassini mission, which orbited Saturn from 2004 to 2017, also made gravity measurements of that planet. And when scientists analyzed Cassini's data in light of Juno's discoveries at Jupiter, they found hints that Saturn too might have a dilute core. If both Jupiter and Saturn have fuzzy cores, that suggests this isn't the result of a rare, catastrophic event like a giant impact. It suggests that dilute cores might be a common, perhaps even typical, feature of gas giant planets. So if a giant impact can't explain the dilute core, what can? This is where we need to consider other processes that might occur naturally within Jupiter. One possibility that scientists have been investigating for decades is something called helium rain. Yes, you read that correctly. It might be raining helium inside Jupiter. Now, this isn't rain in the sense you're familiar with. There are no clouds and no droplets falling through air. But there is a process by which helium separates from hydrogen in Jupiter's interior and sinks toward the center, releasing energy in the process. And this phenomenon might be intimately connected to the mystery of Jupiter's dilute core. To understand helium rain, we need to talk about what's happening deep inside Jupiter. Remember that at certain depths, the pressure becomes so intense that hydrogen transforms into metallic hydrogen, where it behaves like a liquid metal. This transition happens at pressures around 1 to 2 million times Earth's atmospheric pressure, which occurs at a depth of about 6,000 to 8,000 kilometers below Jupiter's cloud tops. Now, at the temperatures and pressures where metallic hydrogen exists, something interesting can happen with helium. Helium, which makes up about 15% of Jupiter's atmosphere by mass, normally mixes well with hydrogen. But in the metallic hydrogen region, under certain conditions, helium can become immiscible with hydrogen. Immiscibility is the property that makes oil and water separate into distinct layers. When helium becomes immiscible with metallic hydrogen, helium atoms begin to clump together, forming tiny droplets. And because helium is denser than metallic hydrogen under these conditions, those droplets sink. Imagine billions upon billions of tiny helium droplets, each microscopic but collectively enormous in mass, slowly settling through the metallic hydrogen layer like snowflakes falling through air. Except instead of snowflakes, it's liquid helium. And instead of air, it's liquid metallic hydrogen. And instead of falling gently, they're sinking through a material that's under pressures of millions of atmospheres. As these helium droplets sink, they release gravitational potential energy, which gets converted to heat. This is exactly the same process that heats your hands when you rub them together. Motion creates heat through friction and pressure. The helium rain thus provides an additional source of internal heat for Jupiter, supplementing the heat that's left over from the planet's formation. Why do scientists think helium rain is happening in Jupiter? Multiple lines of evidence point to it. First, observations show that Jupiter emits more heat than it receives from the Sun. Specifically, Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight. This excess heat needs to come from somewhere. Some of it is primordial heat, energy left over from Jupiter's formation that's slowly leaking out. But detailed calculations suggest that primordial heat alone can't fully account for Jupiter's observed luminosity. There needs to be an additional heat source. Helium rain could provide that additional heat. Second, measurements of Jupiter's atmospheric composition made by the Galileo probe in 1995 when it plunged into Jupiter's atmosphere showed that Jupiter's atmosphere is depleted in helium compared to the Sun. The Sun's atmosphere is about 27% helium by mass, but Jupiter's upper atmosphere is only about 18, to 20% helium. Where did the missing helium go? The most likely explanation is that it sank into the interior. Helium rain would deplete the upper atmosphere of helium while enriching the deeper layers, exactly as observed. Third, theoretical calculations and laboratory experiments have shown that under the conditions of temperature and pressure found in Jupiter's interior, helium phase separation, the formation of helium droplets, is physically possible and even likely. In 2020, scientists at Lawrence Livermore National Laboratory published results of experiments where they compressed mixtures of hydrogen and helium to extreme pressures using powerful lasers. They found experimental evidence supporting the prediction that helium would separate from hydrogen under Jupiter-like conditions. The experiments were technically remarkable, compressing the samples to pressures between 60 and 180 gigapascals, millions of times atmospheric pressure, and observing how the material behaved. The results matched theoretical predictions. Helium rain is real. But what does helium rain have to do with Jupiter's dilute core? Here's where things get interesting. Scientists think that helium rain might not be the only thing sinking through Jupiter's interior. Along with helium, other heavy materials might also be transported downward. Or conversely, helium rain might affect the way heat is transported, which could influence how heavy elements are distributed. Let's consider a few scenarios. First, neon. Another element that's depleted in Jupiter's upper atmosphere dissolves readily in helium. So as helium droplets sink through the planet, they might carry neon with them, further enriching the deep interior in heavy elements. Second, helium rain changes the thermal structure of Jupiter's interior. As the helium droplets sink and release heat, they create a layer where heat is being generated continuously. This can affect the convection patterns in the planet, changing how material circulates. If the helium rain creates a stably stratified layer, a region where the density increases smoothly with depth in such a way that convection is suppressed, that could trap heat and heavy elements in the deep interior, preventing them from mixing or settling. Third, the presence of helium rain might create a situation where the traditional picture of distinct layers doesn't apply. Instead of having a sharp boundary between a core and an envelope, you might have a gradual transition, with composition and density changing continuously from the center outward. This could naturally produce something like a dilute core. The details are complex and depend on things that are difficult to measure or calculate. How much helium is actually sinking? How fast? What's the exact composition of Jupiter's deep interior? How does the equation of state, the relationship between pressure, temperature, and density, behave for these exotic materials under such extreme conditions? These are questions that push the boundaries of our scientific understanding. Recent research has added fascinating details to this picture. In September 2024, a team led by Steve Markham and Tristan Guillot published a study examining the structure of the helium rain layer in both Jupiter and Saturn. They found something surprising. Because Jupiter is more massive than Saturn, its interior reaches the pressures needed for helium phase separation at shallower depths relative to the planet's total size. This means that in Jupiter, the helium rain layer might be relatively thin, just a few tens of kilometers thick, rather than the thousands of kilometers that some models had predicted. The reason is that heat has to be transported through this layer somehow. If heat is transported primarily by diffusion, by heat slowly spreading through the material without the material itself moving, then you need a large temperature gradient, and that means a thin layer. In contrast, Saturn, being less massive, has its helium rain occurring deeper in the planet, where a larger fraction of Saturn's mass lies above the helium rain layer. In Saturn, the latent heat released by the sinking helium droplets might be sufficient to transport nearly all of the planet's internal heat flux. This would allow Saturn to have a much thicker helium rain layer, potentially thousands of kilometers thick, with a much gentler temperature gradient. These differences might explain why Jupiter and Saturn have such different magnetic field characteristics, since the magnetic field is generated in the electrically conducting layers of the interior, and a stable, non-convecting helium rain layer would affect how that field is generated. They might also explain why both planets appear to have dilute cores. If the helium rain creates stable layers that trap heavy elements and prevent them from settling, you'd naturally end up with extended diffuse cores rather than compact ones. So we have two main competing explanations for Jupiter's dilute core. The giant impact hypothesis suggests that a dramatic collision in Jupiter's youth shattered its core and created the dilute structure. The helium rain and internal processes hypothesis suggests that ongoing processes within Jupiter, possibly combined with unusual conditions during its formation, created and maintained the dilute core over billions of years. Which one is correct? As of today, the scientific community is leaning away from the giant impact explanation and toward internal processes, especially in light of the 2025 simulations that showed impacts don't produce stable dilute cores. But this doesn't mean the question is settled. Science doesn't work by consensus alone. It works by evidence, by testing predictions, by finding new observations that can distinguish between competing theories. And there's still a lot we don't know about Jupiter's interior. The equations of state for materials under the extreme conditions in Jupiter's interior are uncertain. The efficiency of different mixing processes is uncertain. The exact composition at various depths is uncertain. These uncertainties leave room for different interpretations of the data. Let me give you a sense of just how uncertain some of these things are. The equation of state, which tells you how a material behaves under different pressures and temperatures, is crucial for building models of planetary interiors. For simple materials like pure hydrogen or helium, scientists have made great progress in calculating equations of state using advanced quantum mechanical simulations. These calculations involve solving the equations that govern how electrons and atomic nuclei behave, which can be done on powerful computers, but requires enormous amounts of computation. But Jupiter's interior isn't pure hydrogen or helium. It contains heavier elements, mixtures of different materials, possibly exotic compounds that don't exist anywhere on Earth. The equation of state for these mixtures, especially under the pressure and temperature conditions in Jupiter's interior, is much more uncertain. Small changes in the equation of state can lead to significant changes in the predicted interior structure. Similarly, the question of how different materials mix or separate under these extreme conditions is complex. Do silicate rocks dissolve in metallic hydrogen? How miscible is water ice with metallic hydrogen? These aren't easy questions to answer, either experimentally or theoretically. Laboratory experiments can only access a limited range of conditions. Computational methods have their own limitations and uncertainties, so when scientists build models of Jupiter's interior and try to match those models to Juno's gravity measurements, they're working with equations of state and mixing properties that have significant uncertainties. Different assumptions lead to different interior models. Some models might prefer a more compact core. Others might prefer a more extended, dilute core. The challenge is to narrow down these uncertainties and converge on a more definitive answer. One way to reduce these uncertainties is through additional observations. Juno continues to orbit Jupiter, collecting more gravity data with each pass. With more data, scientists can refine their estimates of the gravity field coefficients, reducing the uncertainties and potentially revealing features that weren't apparent in the initial measurements. Juno is also measuring Jupiter's tides, the slight deformations that occur due to the gravitational pull of Jupiter's moons. These tidal measurements provide additional constraints on Jupiter's interior structure, because how much the planet deforms depends on how stiff it is, which in turn depends on its internal composition. And in future missions, we might be able to use seismology on Jupiter. Just as seismologists study Earth's interior by analyzing how earthquake vibrations travel through the planet, planetary seismologists can potentially study Jupiter's interior by detecting oscillations, vibrations where the entire planet rings like a bell. Jupiter does have these oscillations called normal modes, caused by convection and other dynamic processes in the interior. If we could detect and measure these oscillations precisely, we could learn a great deal about Jupiter's interior structure, because different structures would produce different oscillation patterns. Juno has actually detected hints of these oscillations in its gravity data, suggesting that they might be observable. Future missions with dedicated instruments might be able to measure them more precisely. There's another fascinating aspect to this mystery that's worth discussing. The implications extend far beyond Jupiter itself. Understanding how Jupiter formed and evolved is crucial for understanding the entire solar system. Jupiter's gravity has shaped the orbits of every other object in the solar system. The asteroid belt structure, the orbits of the outer planets, the populations of comets and asteroids, all have been influenced by Jupiter. If Jupiter formed differently than we thought, if it experienced a giant impact early in its history, that would have had cascading effects on the rest of the solar system. Similarly, understanding gas giant interiors is crucial for understanding exoplanets. Since the first exoplanet orbiting a Sun-like star was discovered in 1995, astronomers have found thousands of planets orbiting other stars. Many of these are gas giants, some even more massive than Jupiter. We can measure basic properties of these exoplanets like their mass and radius, but we can't directly observe their interiors. To understand what they're made of and how they formed, we rely on models. But those models are built on our understanding of planets in our own solar system, especially Jupiter. If our understanding of Jupiter is wrong or incomplete, that affects our interpretation of exoplanet data. For example, many exoplanets have been found on very close orbits to their stars, the so-called hot Jupiters. These planets likely migrated inward from where they formed farther out. Understanding the migration history requires understanding how gas giants form and how they interact with the protoplanetary disk. If giant impacts are common in gas giant formation, that might affect migration patterns. If dilute cores are typical, that tells us something about the formation process and the materials that were available in the protoplanetary disk. Scientists are also finding that the diversity of exoplanets is much greater than the diversity in our own solar system. There are planets that don't fit neatly into our terrestrial versus gas giant categories. Super-Earths, planets more massive than Earth but less massive than Neptune, are extremely common around other stars but don't exist in our solar system. Mini-Neptunes, planets with thick hydrogen and helium atmospheres but not as massive as Saturn or Jupiter, are also common. Understanding the full range of possible planetary structures and formation pathways requires studying a variety of planets in detail. Jupiter, being the closest and most massive gas giant we have, provides a crucial data point. Every discovery about Jupiter informs our understanding of planets in general. The mystery of Jupiter's dilute core is thus not just about one planet. It's about how planets form, how they evolve, and what structures are possible under different conditions. It's about testing our physical theories in the most extreme environments nature provides. It's about expanding human knowledge to encompass phenomena that don't occur anywhere on Earth but are common throughout the universe. Let's step back and consider what we've learned so far. Jupiter, the solar system's largest planet, has a core that's not at all what scientists expected. Instead of a compact ball of rock and ice at the center, Jupiter has a diluted core where heavy elements are spread throughout a huge region, extending to nearly half the planet's radius. This structure is puzzling because it shouldn't be stable. Over billions of years, those heavy elements should have sunk to the center, forming a compact core, yet they haven't. Scientists have proposed several explanations. The giant impact hypothesis suggested that a collision with another massive planet early in Jupiter's history shattered the core and created the dilute structure. This was an attractive explanation, dramatic and plausible, given the chaotic early solar system. But recent, more sophisticated simulations have cast doubt on this idea, showing that impacts don't produce stable dilute cores. Instead, scientists are increasingly looking at processes within Jupiter itself, like helium rain, to explain the observations. Helium phase separation, where helium droplets form and sink through metallic hydrogen, could affect heat transport and the distribution of materials in Jupiter's interior. These processes might naturally produce and maintain a dilute core structure, but the details are complex and depend on physics that's difficult to study or calculate precisely. So the mystery isn't fully solved. We're in a position where we have good observations from Juno, multiple theoretical frameworks, and still significant uncertainty about which explanation is correct. This is actually a common situation in science, especially planetary science. We're trying to understand objects that are remote, inaccessible, and exist under conditions we can barely recreate or model. we have to piece together the story from limited clues, like detectives reconstructing a crime scene from fragmentary evidence. And as with any good detective story, sometimes the clues lead in unexpected directions. But this is also what makes the research so exciting. We're not just confirming what we already knew, we're discovering genuinely new and surprising things about one of the most prominent objects in our solar system. Jupiter has been observed for centuries, studied intensively for decades, and yet it still holds secrets that challenge our understanding. This mystery also highlights the value of space missions like Juno. Building and flying such a spacecraft is expensive, complex, and risky. It took years of planning, engineering, testing, and then a 5-year journey to Jupiter. The mission operates in one of the most hostile environments in the solar system, with intense radiation that limits its operational lifetime. Yet the scientific return has been immense. Juno's gravity measurements revealed a fundamental feature of Jupiter's interior that we had no way to observe from Earth. Without Juno, we might still think Jupiter has a compact core, and we'd have no reason to question our models of planet formation. The mission has opened up new avenues of research and sparked debates that will take years to fully resolve. There's another dimension to this story that's worth exploring: the psychological and sociological aspects of how scientists react to surprising discoveries. When Juno's first gravity results were published, the scientific community had to grapple with data that didn't fit expectations. Some scientists immediately began proposing new explanations, like the giant impact hypothesis. Others looked for ways to modify existing models to accommodate the observations. Still others questioned whether the data was being interpreted correctly. This is normal and healthy scientific debate, but it's also fascinating to observe how personal investment in particular theories can influence how scientists react to new information. Those who had spent years developing detailed models of Jupiter's interior based on the compact core assumption had to confront the possibility that their models were fundamentally wrong. That's not an easy thing for anyone to accept. Yet science progresses precisely because it's a collective enterprise where ideas are tested against evidence, not against authority or personal preference. One person's cherished theory can be overturned by someone else's observation, and that's not only accepted, but celebrated as the way science should work. The story of Jupiter's dilute core is still being written. Juno's extended mission continues to collect data. Scientists continue to develop better models and run more sophisticated simulations. New laboratory experiments are probing the behavior of materials under Jupiter-like conditions. Theoretical physicists are working on better equations of state and better understanding of exotic matter under extreme pressures. Future space missions will add to our knowledge. ESA's JUICE mission, which launched in April 2023 and will arrive at Jupiter in 2031, will study Jupiter and its moons with a suite of instruments. While JUICE's focus is primarily on the icy moons Ganymede, Callisto, and Europa, it will also make observations of Jupiter itself that complement Juno's measurements. The combination of data from both missions will provide an even more complete picture of the Jovian system. Additionally, NASA's Europa Clipper mission, which launched in October 2024, will conduct detailed studies of Europa, including gravity measurements that will reveal that moon's interior structure. Understanding the moon's interiors and how they interact tidally with Jupiter provides additional constraints on Jupiter's internal structure. And looking further ahead, there are proposals for even more ambitious missions. One idea is a probe that would descend into Jupiter's atmosphere, similar to the Galileo probe, but going deeper and lasting longer. Such a mission could directly measure the composition at greater depths, providing crucial data on what materials are present and in what abundances. There are also proposals for missions that could orbit Jupiter for years or even decades, continuously monitoring the planet's magnetic field, auroras, and atmospheric dynamics, and making increasingly precise measurements of its gravity and tides. These missions are challenging and expensive, but the scientific payoff would be enormous. In the meantime, there's also much to learn from studying other giant planets. Saturn, as we've mentioned, also shows evidence of a dilute core. The Cassini mission provided a wealth of data about Saturn, and scientists are still analyzing that data years after the mission ended. Uranus and Neptune, the ice giants, are less well studied but equally interesting. Both planets likely have very different interior structures compared to Jupiter and Saturn, with proportionally more heavy elements and less hydrogen and helium. Future missions to the ice giants are under consideration, and data from these missions would provide important comparative context for understanding gas giant interiors in general. One particularly exciting possibility is that by studying a variety of planets in our own solar system, we can develop a more robust and general theory of planet formation that applies not just to our solar system, but to planetary systems around other stars. This is one of the grand goals of planetary science, to understand planets well enough that we can predict what kinds of planets will form under what conditions, and to use observations of exoplanets to test and refine those theories. Let's consider the timescale question again, because it's central to understanding the mystery. Jupiter is 4.5 billion years old, the same age as the solar system. That's an extraordinarily long time. For comparison, Earth is also 4.5 billion years old, and in that time continents have formed and been destroyed. Oceans have appeared and disappeared. Entire mountains ranges have risen and eroded away. And life has evolved from single-celled organisms to the incredible diversity we see today. 4.5 billion years is enough time for almost anything to settle into an equilibrium state. Yet Jupiter's core apparently hasn't settled. The heavy elements remain spread out across a huge region, rather than sinking to form a compact core. How is this possible? One answer is that the timescale for the core to settle might actually be longer than 4.5 billion years. If the viscosity of the material in Jupiter's interior is high enough, or if the convection is weak enough, materials might move very slowly. In that case, we might be observing Jupiter during a transient phase, where the core is gradually compacting but hasn't finished yet. Calculations suggest that under certain conditions, this could take tens of billions of years, far longer than the current age of Jupiter. So the dilute core might eventually become compact, but not for a long time. Another answer is that there might be processes continuously working to maintain the dilute structure. If helium rain or other mixing processes are constantly stirring up the interior and redistributing heavy elements, then the dilute core might represent a steady state rather than a transient phase. Think of it like a sand castle on a beach. If you build a sand castle and then leave it alone, it will eventually collapse under its own weight and erosion. But if you're constantly repairing and rebuilding it, it can maintain its structure indefinitely. The dilute core might be maintained by ongoing processes within Jupiter in a similar way. A third possibility, and one that's increasingly being considered, is that the dilute core is somehow the natural end state, the equilibrium configuration, for a planet like Jupiter under its specific conditions. Maybe we've been thinking about the problem wrong. We've been assuming that a compact core is the natural state and trying to explain why Jupiter's core is spread out. But what if a dilute core is actually the expected configuration for a planet with Jupiter's mass, composition, and thermal history? This would require rethinking some fundamental assumptions about how materials behave under the extreme conditions in Jupiter's interior. It might mean that our equations of state are missing something, or that the miscibility properties of materials are different than we thought, or that the dynamics of convection and mixing are more complex than current models capture. This is speculative, but it's the kind of question that drives scientific progress. When observations don't match expectations, you have to ask whether the observations are wrong, which is sometimes the case, or whether the expectations are based on faulty assumptions. In this case, the observations seem robust. Juno's measurements have been checked and rechecked, analyzed in multiple independent ways. So the focus shifts to the assumptions underlying the models. Let's talk about what happens next in this research area. As I mentioned, more data will help. Juno's extended mission is providing additional gravity measurements and other observations. These will refine our understanding of Jupiter's interior and might reveal new features or constraints that help distinguish between different theoretical models. In parallel, laboratory experiments are improving our understanding of how materials behave under extreme conditions. Facilities like the National Ignition Facility in the United States and similar installations in other countries can use powerful lasers to create conditions similar to those in planetary interiors, if only for tiny fractions of a second. These experiments are technically challenging and expensive, but they provide invaluable data on equations of state and material properties that can't be obtained any other way. Computational methods are also improving. The simulations of giant impacts and planetary evolution are becoming more sophisticated, incorporating better physics and running on more powerful computers. This allows researchers to test more scenarios and probe the parameter space more thoroughly. Perhaps future simulations will find conditions under which giant impacts can produce stable dilute cores, reviving that hypothesis. Or perhaps they'll confirm that internal processes are the right explanation and help pin down which specific processes are most important. There's also a lot of theoretical work being done on the fundamental physics of matter under extreme conditions. Quantum mechanical calculations, thermodynamic modeling, and statistical mechanics are all being brought to bear on the problem of understanding how hydrogen, helium, and heavier elements behave at the pressures and temperatures found in giant planet interiors. These theoretical advances feed into the models of planetary structure and help reduce the uncertainties. All of this work is interconnected. Observations guide the theory. Theory predicts what should be observable. Laboratory experiments test theoretical predictions. Simulations integrate everything together and make predictions that can be compared with observations. It's a complex web of research activities, all working toward the common goal of understanding Jupiter. And this work doesn't just answer questions about Jupiter. It has broader implications, as I mentioned earlier. Understanding gas giant interiors informs our interpretation of exoplanet data. It affects our understanding of how planetary systems form and evolve. It tests our physical theories in extreme regimes that can't be accessed in any other way. It's fundamental science in the best sense of the term. Now let's zoom out even further and think about what this mystery tells us about the nature of scientific knowledge. Science is often presented as a process of steady accumulation of facts, where each discovery adds another brick to the edifice of human knowledge. And there's truth to that picture. We do accumulate knowledge. We do learn more and more about the universe. But science is also perhaps more fundamentally about confronting and resolving puzzles. It's about finding observations that don't fit our current understanding and then working to expand or revise that understanding. The mystery of Jupiter's dilute core is a perfect example. Before Juno, scientists had a reasonably good understanding of gas giant interiors. Not a complete understanding, certainly, but a working model that seemed to explain most of what we observed. Then Juno provided new, more precise observations that didn't fit the model. This created a crisis, in the technical sense that philosophers of science use that term. Not a crisis meaning everything is wrong and we don't know anything, but a crisis meaning we've encountered a significant anomaly that requires attention. And the scientific community has responded exactly as it should. Scientists have proposed new explanations. They've tested those explanations with simulations and calculations. They've gathered more data. They've revised their models. They've argued and debated and sometimes disagreed. This is science in action, and it's messy and uncertain and fascinating. One thing that's important to recognize is that this process doesn't necessarily converge quickly to a single, definitive answer. Sometimes it takes decades for scientific controversies to be fully resolved. Sometimes the resolution comes from an unexpected direction, a new observation, or a new theoretical insight that wasn't anticipated. And sometimes the resolution is incomplete, leaving lingering questions and alternative interpretations. That's okay. Science doesn't require perfect certainty. It requires that we follow the evidence as best we can, that we're honest about uncertainties, and that we remain open to revising our views in light of new information. The mystery of Jupiter's dilute core is still unfolding. We don't yet know for certain how it formed or why it has remained stable for billions of years. But we're asking the right questions, gathering the right data, and making progress toward understanding. That's what good science looks like. As individual citizens of Earth, we're privileged to live in an era where we can send spacecraft to other planets and peer into their deepest secrets. Just a few decades ago, Jupiter was a distant point of light, Now, we're measuring its gravity field with extraordinary precision and debating the structure of its core. That's an incredible achievement, a testament to human ingenuity and curiosity. And the mysteries we're uncovering, like Jupiter's dilute core, remind us that the universe is far stranger and more complex than we often imagine. So where does that leave us? We've journeyed through the discovery of Jupiter's dilute core, explored competing explanations from giant impacts to helium rain, examined the challenges in testing these theories, and considered the broader implications for planetary science. We've seen how a single spacecraft's measurements can overturn decades of assumptions and spark intense scientific debate. We've grappled with the puzzle of why this structure hasn't settled over billions of years, and we've considered various possibilities from long timescales to ongoing processes to fundamental rethinking of our models. What emerges from all of this is a picture of Jupiter as a far more complex and dynamic world than the simple layered model would suggest. Jupiter is not static. It's a planet where helium might be raining through metallic hydrogen, where ancient collisions might have left their mark billions of years ago, where the boundary between core and envelope is blurred and diffuse rather than sharp and distinct. It's a planet that challenges our understanding and pushes the boundaries of our knowledge. And that's exactly what makes it so fascinating. The greatest discoveries in science often come not when we confirm what we expected, but when we find something genuinely surprising. Jupiter's dilute core is one of those surprises. It's a mystery that will likely occupy planetary scientists for years to come, driving new observations, new experiments, new theories. And as we work to solve this mystery, we'll inevitably make other discoveries, uncover other surprises, and deepen our understanding not just of Jupiter, but of planets in general. The blurred heart of this giant, this mixing of heavy elements throughout such a vast region, is telling us something profound about the history and nature of gas giant planets. We just need to figure out what that message is, and we will. Science has a remarkable track record of solving mysteries, given enough time and effort. The puzzle of Jupiter's dilute core may be challenging, but it's not insoluble. With continued observations from Juno and future missions, with improved laboratory experiments, and better theoretical models, with the dedicated work of scientists around the world, we'll eventually understand how Jupiter got its fuzzy core. And when we do, that understanding will reshape our view of planet formation and evolution throughout the universe. But for now, the mystery endures. A reminder that even the most familiar objects in our cosmic neighborhood can still surprise us, still teach us, still inspire us to look deeper and question further. If you've made it this far, thank you for joining me on this journey through one of modern planetary science's most fascinating puzzles. The story of Jupiter's dilute core is still being written, and every new observation, every new theory, every new experiment adds another chapter to that story. It's a story about the largest planet in our solar system, but it's also a story about how science works, how we push the boundaries of knowledge, and how we respond when nature surprises us. If you enjoyed this deep dive into the mysteries of Jupiter, please give this video a like. It really helps the channel grow and lets me know that you want more content like this. And if you haven't already, make sure to subscribe so you don't miss future explorations of the universe's most intriguing questions. We'll be covering topics from the formation of the first stars to the nature of dark matter, from the possibility of life on other worlds to the fate of the universe itself. There's so much out there to discover, so many mysteries to explore, and I'd love to have you along for all of it. Until next time, keep looking up, keep asking questions, and keep wondering about the incredible universe we're privileged to inhabit. The blurred heart of Jupiter is waiting for us to understand it, and somewhere out there, other mysteries are waiting to be discovered. Thanks for watching.